We've got a busy day today, so go ahead and make sure that you have your standard reduction potentials chart out from the references alongside your half reactions slides that you've already copied. We are going to be looking at almost entirely brand new stuff all unit long. It's going to be this first tiptoe at the beginning that might contain some items that you are familiar with, which would be great. But what we have to do to get to cell potential, which is the real electrochem calculation that we want to do, is we need to do 2 baby steps to make sure that we understand some foundational stuff. So, diving in. Let's start with redox reactions. Redox reactions have a couple layers to them. You should have covered them in pre-AP a little bit, where we need to look at the definitions of oxidation and reduction. So have this slide handy because you're going to want to be referring back to it during these first 15 minutes. But redox reactions are made of reduction and oxidation reactions that are complementing one another. Some funny things happen in regards to oxidation states in these redox reactions. You probably remember that oxidation states are somewhat synonymous with predicted charge. Like if I were to say, what's the oxidation state of lithium? You would probably say +1 because that is lithium's predicted charge, thus its normal oxidation state. And while that is true most of the time, it's not always true. Sometimes in compounds, especially those involving polyatomic ions, the oxidation states can do weird things. Now, I gave you these rules, and really, if you look over most of them, they're familiar to you. They actually match what the periodic table says in most cases. Our issue comes when you run into elements that are not on this rule sheet because they can be wildcards in regards to a wide range of oxidation states. So I'd like to do a couple simple practice problems with you. Have that table I just showed you in front of you, and let's work through this page together. So let's start by examining nitric acid. So there's my nitric acid, and what my problem wants us to do is find the oxidation state of each part of that compound. All right, here's my methodology for doing so. I'm going to break it into its parts, and I'm going to count the number of atoms of each. I want to multiply that count by the oxidation state. What I like to do is draw these boxed off areas. The main reason being is that you're going to end up with several numbers in front of you, and I want your brain to easily be able to see what the answer is. I'm going to be putting the oxidation states into these brown boxes. Now, here's where your knowledge comes into play, because if you look at that new table about oxidation states, hydrogen in this situation is always +1, just like you expect it to be. Oxygen in this situation is always -2, just like you expect it to be. It's nitrogen that doesn't have a set rule and that you'll discover has a funky oxidation state here. 1 times 1 is 1. And 3 times -2 is -6. What I know about this compound is that altogether, the overall charge is 0. Look at nitric acid. It has no net charge. Therefore, what must the overall charge of nitrogen be? It must be +5. Now, that's not necessarily the answer, because the oxidation states are going into the boxes. 1 times what is positive 5? Positive 5, so this time it is. And now I've got the oxidation states of every member of the compound. Let's do another. Check out magnesium sulfate. I hope your formula writing skills are up to par. Let's break them apart. I'll count 1, 1, 4. By following my rules, magnesium in this situation is always +2 as expected. Oxygen is -2 as expected, but sulfur does not have a solidary rule to follow. 1 times 2 is 2. 4 times -2 is -8. And again, we are looking for an overall charge of 0. So what must sulfur be here? +6. Makes the number sentence true. And 1 times +6 is +6. I know it didn't happen in my examples, but keep in mind, if there were 2 sulfurs, what would the charge have been in this if the rest of the number stayed the same? +3, right? Because it would be 2 times what equals +6, and that would alter that. So make sure you are checking the number sentence fully, because it won't always be a 1. Another thing I want to point out is this total charge at the bottom does not always have to be 0. For example, if it was phosphate that you were analyzing, well, phosphate is PO4 -3. Therefore, the overall charge would be -3. All right, and you would do all the same stuff. It's just these numbers would need to add up to that other non-zero charge. Another idea to add to your notes is that oxidation states can be decimal numbers. Oxidation states can be decimal numbers. For example, what if it was 4 oxygens, but I needed the total over here to equal 10? Well, 4 times what is 10? 2.5, right? You just take 10 divided by 4 and it'll give it to you. All right, but that would be a viable answer. And Schoology is going to practice all these angles. We just don't have time to look at them all now. There's another problem on that same slide that takes us a step further into actual redox. Let's work on it. lithium and strontium nitride. So we've got lithium reacting with strontium nitride, giving us strontium and lithium nitride, it looks like. All right, we're not balanced, and I mean, we should be, but we don't have to be for this simple redox analysis. Look back at slide 1. Have the vocabulary from slide 1 handy. And what you'll see is that redox, reduction and oxidation, is really a focus on electron movement. If we want to know who's oxidized, losing electrons, and who's reduced, gaining electrons, all we have to do is compare the charges of species as reactants to the same species as products. And if we know what the charge does, then we know what the electrons do. So let's analyze this reaction. I'm going to make my list again. We've got lithium, strontium, nitrogen. I'm only going to focus on their current oxidation states for charge, but here's an idea that you may have forgotten. It's on the table from the second slide, but you might want to write that free elements have oxidation states of 0. Free elements, unbonded, have oxidation states of 0. Like, look at lithium there. Do you see how lithium is all by himself as a reactant? Automatically an oxidation state of 0. Strontium is +2 as expected. Nitrogen is -3 as expected. So there's the reactant values. Let's compare them to the product values. Lithium as a product has his +1 charge. Strontium as a product is a free element, and all free elements are 0. Nitrogen as a product is still -3 bonded. He remains unchanged. Again, look at the definitions from slide 1. To be reduced is to gain electrons. To gain electrons is to become more negative. Who became more negative? Strontium. His number went down. To be oxidized is to lose electrons. To lose electrons is to become more positive. Who became more positive? Lithium. His number went up. Nitrogen did not do anything with his electrons, so who cares? Now, there is some muddy water vocab also going on slide 1, because there is a secondary terminology that AP can use to mess you up. If you're the item being reduced, all right, you see how strontium was reduced? If you're the item being reduced, you're also the reason that the other guy was oxidized, all right, because you took his electrons. If you're the item being oxidized, all right, you're the reason that the other dude was reduced, all right, because you gave him your electrons. The secondary term, as you can read off your slides, is that whoever's reduced is also known as the oxidizing agent. Because he oxidized him since he was reduced. Whoever's oxidized is the reducing agent. Because lithium reduced strontium. You'll notice they're just opposites, but if you're not careful, you can do the analysis correct and then draw the opposite conclusion. So be careful on the wording of the questions, on what exactly it wants. Does it want to know who is reduced, or does it want to know who's the reducing agent? Because those are two different dudes. So that was our first of two baby steps towards real electrochem. And that was the easier one, sorry. In this unit, our big focus is going to be the variable E, which stands for cell potential. Cell potential is going to be a voltage that we care about to describe whether reactions will happen spontaneously or non-spontaneously, thermodynamically favored or not. Now, while we are studying standard conditions, studying standard conditions of cell potential, our standard now is still going to be 1 atmosphere. We're back to room temperature, and it's added a molarity. Standard molarity is 1 molar. The other baby step that we need in order to do this is to understand that cell potential is built off of redox, which we just covered, but it's the redox of half reactions, which is something that is new. A half reaction analysis can be complicated to learn. All right, it's kind of, it makes me think of stoichiometry. When I first teach stoichiometry to smart kids, at first it takes them a while to actually grip what's happening and why. But then once they have it, it makes sense what we're doing. Half reactions are going to be the same way, because what I've provided you is every step you need. All right, if you can read steps, you can do this. It's just there's a lot to think about. All right, so these two examples we're going to do, they're going to feel a little hairy, and I'm sorry. All right, but of course, practice makes perfect. We'll get good at it, but just absorb the best you can, and don't freak out on me. All right, but this is not the most fun thing to do in the world. So let's just dive in head first. Have those rules in front of you, because I'm going to go straight down. But we're going to do two half reaction analyses so that we can really get ready for cell potentials. Now, in these two problems, you'll notice that one is in an acidic solution and one is in a basic solution. All right, it will just always tell you that one way or the other. But the reason that's important to know is that if you look at the list of rules, acids have a list of rules, acidic solutions. Bases have the same list of rules, plus a step. So basic solutions are more annoying, but I want you to understand what's happening. Let's do the first problem. Step 1 says identify the two half reactions. It turns out that our redox reactions are going to have two simultaneously occurring half reactions that we want to examine, all right? We're going to examine them individually and then we'll put them back together. Step 1 says separate the reaction into the two half reactions. Now this part will take a bit of practice just seeing it, all right? But one of the reactants is going to connect directly to one of the products, and it will happen like that twice. So watch me pull out two half reactions from this first problem. All right, first I see MnO4 minus. And I'm going to connect that reactant to Mn plus 2. They got stuff in common. The other half reaction, all right, I'm going to write it down here, is going to be the H2C2O4. H2C2O4. And he's got stuff in common with carbon dioxide. All right. Now, listen, I'm going to go through steps 2 through 5 on each half reaction individually. So I'm only, for the next couple minutes, going to focus on the first half reaction while going through the next few steps. We need to balance everything. The trick is, I mean, you know how reactions work. It needs to be the same on both sides, all right? And you can see right now, we have oxygen on the left and no oxygen on the right on the first half reaction. That should already mess with you, all right? Let's fix it. Step 2, reading off the prior slide, says, balance what you already see. Now, there's nothing I can do on the top one because the manganese are already balanced. There's one of each, and we're completely missing oxygen from one side. So there's no coefficients I can add at this exact moment on the first half reaction. Step 3 says add water to the side with less oxygens. Okay. Oxygen, no oxygen, add water. And I can use that water to fix the oxygens. See how there's 4 oxygens there? Let's make there be 4 oxygens there. Hooray, the oxygens are fixed. Step 4, add hydrogens to the side that needs hydrogens, all right? See how we have a bunch of hydrogens over here? Let's fix them. Let's add some hydrogens over here. How many do we need over here? Nope, 8. I'm just happy to hear a voice. Yep, we need, like, there's 8 and there's 8, hooray. Now the hydrogens are fixed. Just like, I'm just going straight down the steps. Step 5 is something brand new. Step 5 says balance the charges. That's something we haven't really had to think too much about in here. We need there to be the same charge on both sides of the reaction. Let's start by looking at what charge we currently have on each side. All right, here's what I see. I see 8 pluses and 1 minus, giving me a charge of +7 on the reactant side. 8 pluses and 1 minus has a net charge of +7. What about on the right-hand side? +2, nothing, so just +2. Now, on this step, we are adding electrons to make them equal. Think about what adding electrons does. Adding electrons makes things more negative. So the only side that we're going to focus on is the side with the higher charge so that we can add electrons to bring it down to whatever the heck the charge is on the other side. In other words, I need to bring the +7 down to a +2. How many electrons do I need? 5. Let's add 5 electrons. And now everything is perfectly balanced on the first half reaction. All right, now we need to reverse because we need to do those same steps we just did for the other half reaction. So rewind back to step 2. Hey, we didn't do anything for step 2 a moment ago. We skipped it because there was nothing to do. That's not the case here. Step 2 says balance what you can before you start adding stuff. We can do that this time. Look. I mean, there's no hydrogen over there, which is gonna, we'll fix that in a minute. But we can fix the carbons and oxygens right away. If I put a 2 here, now there's 2 carbons and 4 oxygens. So that's a listed step. Don't skip that. All right. Usually this step doesn't work out, but it did this time. All right, but we're not done. Those hydrogens suck. So let's go to number 3. It says add water to fix the oxygens. Our oxygens are good. We have 4 oxygens on each side. We don't need to do that. We don't have to add water if there's nothing to fix. Step 4, add hydrogens. We do have a hydrogen issue because we got 2 there and none there. So let's add hydrogen. And we have fixed our hydrogen problem. Step 5, balance the charge. All right. Hey, look, there is no charge over here. All right, there's nothing. It's just neutral. All right, that's also nothing, but we have 2 pluses over here. So what do I need to add to fix the charge? 2e negative, right? We can only make things go down. So I want my +2 to drop to a 0. So let's also add 2 electrons. And we have done the first 5 steps completely. All right, new zone though. Look at step 6. A little different, yo. Here's the deal. Listen, the number of electrons in each half reaction have to be the exact same. The number of electrons in each half reaction have to be the same. How do you do that? Just multiply them so that they are. Multiply the reactions so that the number of electrons are the same. I've got 2 there and 5 there. What is the lowest common multiple of 5 and 2? 10. Let's fix it. I'm going to multiply the top reaction by 2. The whole reaction, I'm going to multiply by 2. All right, if I do that, 5 times 2 is 10. 8 times 2 is 16. All right, put a 2 there, and put a 2 there. And 4 times 2 is 8. I just multiplied everything by 2. What's my goal? To make the electrons the same. Remember, we're getting the 10 electrons, so the bottom equation is going to be multiplied by... Very good. Let's multiply the bottom equation by 5, which is going to put a 5 here, a 10 here, and a 10 here, and a 10 here. Stop me if you need to. I'm happy to answer questions. Step 7, the last step, since it's acidic, says that we're going to combine them back into a single equation. Now that's great, but careful, because when you're recombining them, anytime 2 things match from your 2 half reactions, they will cancel out. Now understand the way they're canceling out, all right? If I have 10 carbons on one half reaction and 7 carbons in another one, I'm going to end up with 3 carbons in only one of them. Listen again. If I have 10 carbons and 7 carbons, the 7 carbons are going to go away completely, and 7 of those 10 will also go away, leaving me with 3 carbons in that one section. That's the way they cancel out. Watch it happen. Hey, see the 10 electrons in the 10 electrons? That's perfect. Boom, they gone. That will always happen with electrons because, I mean, we made that happen, right? But look at the hydrogens. There's 16 and 10. How many are going to be left? No, there's not for that one. There's only 1. 6. Perfect. All right? Because all 10 of those are going to go away, and 10 of those will go away, leaving me with 6 H pluses as a reactant. These guys are gone. And then just list, what's my next reactant? 2 MnO4s. We're just putting them all together. All right, my next reactant is 5 H2C2O4s. My first product is 2 Mn plus 2s. My next product is 8 waters. My next product is 10 carbon dioxides. That's it. We're done. A lot happened there, but you'll get good at it since I have the steps written for you. But let's do another one from scratch for your brain. Now, this next one is in a basic solution, so you'll see there's a bonus step. Let's worry about that when we get there. You feeling good? Step 1, find the half reactions. All right, let's find the things in common from reactant to product. All right, this one's pretty easy. I see BrO3 minus. We're going to connect that dude to Br minus. There's one half reaction. I see iron 2. And iron 3. There's my half reactions. Let's analyze the top one first. Step 2 says balance everything. It's balanced as much as I can. One bromine, and the oxygens are out of whack. Step 3, add water to balance the oxygens. Add water, and now I can balance the oxygens. 3 oxygens on each side. Step 4, add hydrogens. All right, so we're going to add some hydrogens to the other side. I need 6 of them. Step 5, balance the charge. My charge here is 6 pluses and a minus. Makes this side +5. Over here, it's just a minus, so it's a -1. What do I need to add to make a +5 drop to a -1? Six electrons. Ask questions if you got them. All right, so we're good there. Let's do the next one down in the next half reaction. Step 2, balance any atoms you can. 1 iron, that's good. Step 3, fix the oxygens, there are none. Step 4, fix the hydrogens, there are none. Hooray! We get to skip those steps because nothing is out of balance in regards to those even existing. But the charge is wrong. I need a +3 to become a +2. I'm adding 1 electron. All right. Step 6, we need the number of electrons to be the same. The number of electrons must be the same in both half reactions. 6 and 1, I only have to multiply one of the reactions to do it this time. Let's multiply the bottom one by 6. So times 6. 6, 6, I won't say it because, you know. Let's combine the reactions, all right? You'll notice that the only thing that cancels out this time are the 6 electrons, and everything else is going to come down. So let's do that, 6 H pluses. All right, and then BrO3 minus and 6 Fe2s and bromine ion and 3 waters and 6 iron 3s. Last time, we were done right here. This time, we're not, because my solution is being described as basic. So go back to your rules, and you can follow along with how we fix this. The reason I know it looks wrong is because the basic solution is not going to have this acidic character right here. See those H pluses? No, 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 no. Those can't be there. How do you get rid of H pluses? What makes H pluses go away? OH minuses, all right? So really, if we just counteract those 6 H pluses with 6 OH minuses, they go bye-bye. So let's do that. Let's add 6 OH minuses. And that will make it not be acidic anymore. Mainly because whatever you do to one side to keep it balanced, you got to do to the other side. Which means to fix that, we're also adding 6 OH minuses over there. Now, this isn't just a canceling out, all right? It's a combining of. Because OH minuses don't make H pluses disappear. They neutralize them. And what's created during neutralization? Water. So we're not making there be nothing. We're putting H's with OH's and making 6 waters. Now that's fine. All we have to do is rewrite this with the updated equation and we're done. But the creation of 6 waters is going to reactivate for a moment the idea of canceling stuff out. Because if I have 6 waters on the left and 3 waters on the right, they need to do that cancel out thing we did a moment ago. How many waters will be left? On which side? You're my favorite today. Yeah, he said 3, because what's going to happen is we have 6 waters here and 3 waters there. These 3 waters will go bye-bye, and we'll be left with 3 waters here. The black writing is the answer. Are you exhausted yet? We're near the end. If we put all of this together, we can begin to calculate cell potential. Now, a couple things I need you to understand. Cell potential, which again is measured in voltage, can be positive or negative, but that sign has major implications for the usefulness of what you are, what system you're looking at. If you want the system you're examining to be spontaneous, to just automatically happen, E, cell potential, has to be positive. A battery, for example, is a cell that is positive. Now, a battery can be a negative E, but you know what we call that? A dead battery, all right? Because positive E means that it has the spontaneous ability to do work. Now, you can have systems that have a negative E, all right? That's fine. We call those electrolytic cells instead of galvanic cells. More on that later this week. But you can have a system with a negative E, but it's just not thermodynamically favored if you do. Meaning, you got to plug it into the wall or something, or put a battery into it with a positive E to overcome the negative E. So that's kind of how we're thinking about the chemical parts of making things work electronically. Look at your reduction table. Let's talk about what the heck is going on here. Again, you don't have to memorize any part of this, and I want to point some things out. It gives you a bunch of reactions, right? These are all the common reactions that you would possibly need to know the solid voltage for. Notice how all of the reactions are reduction. How do I know they're reduction? Because all of them have electrons as a reactant. Reduction, by definition, is the addition of electrons. So it makes sense that, sorry, my computer's about to die. It makes sense that if everything on there is reduction, the electron will always be a reactant. So that's one of the things going on. And then here's the values, the constant values. Now, why would I not give you a table of oxidation values then? Because I won't. The reason you don't have to have a separate table for all the oxidation values is because if you reverse the sign of these voltages, they become oxidation numbers. Meaning, if you're looking at one of these, but you need the electrons to be on the other side, and that's the number you need, then just reverse the sign of E, all right? Make the positive negative or negative positive. So by just being given the reduction, I mean, look, it's titled reduction. You don't have to memorize it. If you're just given all the reduction values, you're also being given all the oxidation values. The other really important thing to understand about the table is that the higher the voltage, the more they want to be reduced. Looking at, since this is reduction, all right? So in this regard, the ones that have the higher numbers are the reactions that are more likely to be reduced than reactions with lower voltage listings, cell potential listings. And that'll be important on one of the types of questions you might run into. So with all that in mind, let's answer 3 different types of questions. I'm not going to do that third one because it's a repeat of it. That's my bad. But we're going to answer 1, 2, and another one so that I can give you, different types. But let's start with the first one. The first one is a common multiple choice type question. It gives you 3 things, and it says, which one is the strongest oxidizing agent? You gotta be really careful there. The whole thing, guys, with this chart is that, yeah, you're gonna be good at reading it when I'm done with you, but the trick is, do you know when to reverse the sign and when not to? Because it's pretty much 50-50. If it's asking you about something being reduced, you don't switch the sign. If it's asking you about something being oxidized, you do switch the sign. What is this question asking? Who is the best oxidizing agent? Are oxidizing agents oxidized or reduced? They're reduced. Remember, it's opposite from when we just started redox earlier this lecture. So they're trying to trick you on whether or not you're supposed to reverse the signs. Since it wants the oxidizing agent, it wants the item being reduced, meaning the values on the paper are correct as is. So here's what we're going to do. We're going to find all three of these, MnO4 minus, Br2, and Ca+2. Let's find all three of them and compare their numbers. Now, we don't have time for y'all to find them all, so I'm going to tell you their numbers, and you could find them real quick and see how I'm doing this. All right, so MnO4 minus has a value of 1.51. Find it. Find the number 1. The numbers are in order. It's everything else that's not. Find 1.51, and you'll see that that is the reaction for the MnO4 minus. So that is his cell potential. The cell potential for the bromine is 1.09. Find 1.09. And you'll see that 1.09 is right there. Sorry, it's backwards on my screen. But there he is, bromine, 1.09. Calcium plus 2 is negative 2.76. Find the negative 2.76, and you'll see that it's living right down here. 2.76. Check it out, it's calcium. So you could have found those, right? They were listed in the question. But the question wants to know which one of those is the best oxidizing agent, which is also asking which one of those is most likely to be reduced, and what's the answer? The higher the number will win. In this case, the answer is MnO4 minus because it has the highest cell potential. Again, the answer is MnO4 minus.
I have a question.
What up?
So for MnO4 minus, there's like multiple reactions with it. How do we know which one to choose?
That's a good question. Look back at the question though. Look back at the actual question. You see how it says in acidic solution?
Yes.
To be in acidic solution, there has to be H pluses visible. Do you agree with me?
Yes.
You see how the one I picked was the only one that's doing that?
Yeah, okay, I see it now.
Yep. Cool. Good question. Okay, let's look at the next one. Will aluminum displace copper in an aqueous solution of copper-2 nitrate? All right, so this one's looking at an entire reaction between aluminum and copper-2 nitrate, so we could write out the whole reaction, and that would be fine. The nitrate is a spectator ion. I know that. It's not going to move anywhere. So I'm going to simplify the way this looks for you a bit. Whoa. It's attached to a chair. Dun. Okay. Will aluminum displace copper-2? Let's find out. Really, what's happening is aluminum, that is not aluminum, we'll astatine for you, all right? Aluminum with copper-2 is what it's asking, all right? It wants to know, will it switch places with that nitrate in there? All right, the nitrate's not moving, let's just focus here. If they were to switch places in a compound, the copper would look like that, and the aluminum would bond and get his charge. The question wants to know, would this happen? Remember, for the reaction to happen, you have to have a positive E, all right? So all we have to do is find the cell potentials of the half reactions, which is on the chart, and find out if the sum of them is a positive or negative number. And that'll tell us if it's spontaneous. All right, so what are the half reactions? Well, let's look. All right, one of the half reactions is aluminum to Al to the Al here. All right, so we've got aluminum yielding aluminum plus 3. There's no O's or H's to worry about like we were doing a moment ago. It's just the charge that we have to balance. So all I need are 3 electrons. And we have followed all of our half reaction rules and it's balanced. The other half reaction is the Cu plus 2 to Cu. I like the Cu. I like the Cu. All right. There's no H's to fix. There's no O's to fix. There's just a charge to fix. All right. So I want the plus 2 to drop down to a 0. I can make that happen like this. All right, so those were some easier half reactions to analyze. But what is E? That's what I care about, all right? So use your chart, find them. You can find these values, all right? My aluminum value for that top half reaction, I get 1.66 volts. Find 1.66 volts. Now, careful because it's not going to look that way on your chart, is it? This is not reduction. Aluminum is oxidation. Look where the electrons are. Remember, I mean, if you learn nothing else today, learn this. If the electrons are on the reactant side, it is reduction. If the electrons are on the product side, it's oxidation. This is oxidation. That chart does not give you oxidation values. But what do you do once you find the reaction? Boop, flip the sign. That's why it's a positive 1.66. The value I get for the other half reaction is 0.34. Will that happen? It will. Because remember, you just add them up. I mean, they're both positive numbers. It doesn't even matter. The way this question's worded, it doesn't even matter what they equal. A positive number plus a positive number is going to be a positive number. So we're good. As long as E is positive, it's thermodynamically favored. Yeah. I don't want to do that third question because it's identical to this one. I mean, I'll let you know that the answer is yes. If you want to work it out, you're going to get yes again. Make sure you can get that. But I want to show you one different type of question that you commonly will run into. I'm short on time. If the bell cuts me off, you'll have to watch the end of this question on the video. Just fast forward to the very end. But I will try to finish it. But here it is. Here's the question I want us to answer together. Is iron 3 capable of oxidizing iodide ion? It's all about the words. It's the way that it's worded that your brain has to be able to dissect who's doing what in the half reactions. All right? Because what I see is that iron is oxidizing iodine. So if iodine is being oxidized, that means that iron must be reduced. All right, and then of course, if iron is reduced there, he'll be Fe plus 2. And just like the words say, iodine ion is being oxidized, which means the electron must be over here on the product side. And if you remove it's oxidized, oxidation is the removal of an electron. If you remove an electron from I minus, you will just become iodine. careful. There's some extra chemistry happening there. All right? I know it's a bummer when I muddy the waters like this, but can iodine uncharged exist by itself? No, no, no. Brinkelhoff won't let that happen. The moment that he's not an ion, he has to follow the diatomic rules. Y'all are welcome to go. I'm really close to them, but y'all are dismissed. Which means that there would be a 2 there, and then there would be a 2 there, and now everything would be balanced. Now, I mean, technically this question doesn't need all that, but sometimes like an FRQ certainly would, all right? But now I have my half reactions that we can analyze, all right? So go and look them up. Now this one is reduction, all right? So what's on the sheet is gonna be correct. And I get a reduction value here of 0.77 volts. Careful, careful, careful. This is oxidation. You need to flip the sign. And when you do, and you look it up, I get negative 0.54. Yes or no?
Yeah.
And this one was closer. However, it'll happen because if you sum those together, our cell potential is positive. And hooray, the answer is yes. Now, I know all the answers were yes. There'll be no just as often, all right? It's better when you don't expect it. You know, y'all always think that I'll show you one of each. So boom, plot twist, all right? Questions on half reactions? See you Wednesday. The room is empty and the mask is off. Everyone has left the Zoom. Now it's just you and me. What you want to talk about? Your joke?
Oh, sorry about that. I was just
oh, dang it!
writing down notes.
Who is it? Who is it? What's up, Simon?
No, I didn't have a question. I was just writing down like the final notes that.
I'm sitting in your way.
Yeah.
I like that. I like that. I didn't actually have a joke at that moment, so you kind of you saved me.
Okay, thank you. Have a nice day, Mr. Cummings.
Adios.